Hi there. Well, what we're going to do is we're going to look at section 8.1. So we finished chapter 3 and we're looking at we'll look at 8.1, 8.2 and 8.3 and then finish up and then have our test. All right, so looking at 8.1. Now what this is going to help you is those of you that maybe were struggling with interval notation, this will be another review of interval notation. And, it is something that Pearson likes. And when you get into your 1400 or your other math classes, it's something that they'll just assume that you know. All right, so in this section, we're going to be looking at graphical solutions and compound inequalities. Now, inequalities are mathematical sentences that contain these inequality symbols. Now, each one is read differently. This one is read less than, because you come to the smaller end first as you read from left to right, greater than, less than or equal, greater than or does not equal, which we've seen this symbol in doing domains, because we know the denominator cannot be 0, so we've used this. All right, so unlike an equation, where there is usually at most a few solutions, the solutions to an inequality, when you have one of these, will oftentimes be an interval. All right, it'll cover a range of solutions, not just certain solutions like an equal sign. Before we look at any solving inequalities, we will talk about some important properties of sets. Okay, so looking at some set notation. To begin with, we're going to look at intersection of sets and conjunctions of sets. They're the same thing, just two ways of writing of meaning the same thing. Now, math, in math, you're learning how to translate from an English to symbols. And it's like learning a foreign language. It's exactly like learning a foreign language. So we're going to be transferring some of these English ideas into symbols. So the intersection of two sets, A and B, is the set of all elements that are in common to both A and B. So this is important. This terminology, that when you find the intersection, you're finding out what's in common to both sets A and B. And let's see, and the symbol we use for an intersection is this kind of upside down U. If you ever need this in Pearson, it'll show up down below in one of the boxes for you to click on. So you don't use a U. So I know you'll need the symbol. Just look for it when you click in the answer box, this will show up. Now an intersection corresponds to the word and. So now if you have intersection, if you have common to both sets A and B, or you see the word and used in certain spots, you'll know that you're talking about an intersection. All right, here, and intersection, common to both, or a conjunction. All right, all of these mean the same thing, and we'll talk about what exactly that meaning is. Intersection, common to both of the sets. You're looking for what's in common. What do they have that's the same? The symbol that we use, instead of writing out the word intersection or the word conjunction, we can use this symbol. And also when and is used in certain spots, it means intersection. So let's go through a bunch of intersections here and then different ideas for intersections. Find the intersection. So they're giving you two sets. Like here we have, your set A and B. So we have a set intersected. Again, they related the symbol with the word. And then here you have another set. So your answer is a solution set. So we'll use our symbols for our set here. Now, Pearson may actually put these in for you. You just have to fill in what goes on the inside. If not, you have these on your computer, on your keyboard, the brackets. All right, so here we have the number 1 in this set. Is there a number 1 in this set? Because we're looking for numbers that are the same. Here's a 1 and there's a 1. So yes, 1 is in the solution because it's in common to both sets. 2 is in this set. 2 is in this set. Okay, so we have the number 2. All right, again, in common. 3 is here, but it's not over here. 4 is in this one, but it's not in this one. 5 is in this set, but it's not in this set, so we do not include it in our intersection, our conjunction. The only numbers that both of these sets have in common that are the same is the numbers 1 and 2. So our solution set, I erase my comma because there weren't any others. The solution set is the set 1, 2. That is our solution to this right here. Okay, let's look at another one. All right, find the intersection of A and B, where A is this set and B is this set of numbers. So we look for what's in common because it's an intersection. So we have 2. 2 is not in here. I just cross it off because I've dealt with it. 4 is not in here. 6 and 6. So we do have one number that's in common. That's the number 6. 8, no 8s. 10, no 10. 12. We have a 12. So we have it in both sections of 12. 14, no 14. So here, the only 2 common numbers between both of these sets was 6 and 12. There's your solution set. 6 and 12 is the solution for the intersection of sets A and B. All righty. Let's look at graphing. If we have a graph, sorry, get that straightened out here. So we want to graph and write the interval notation of the conjunction intersection of -2 is less than x and x is less than 1. Now this first inequality has x behind over here. We're going to switch it and it just makes it so much easier to graph. So we have x is, one second here. All right, so we do want this x to be in front like this one is. It is just easier to read that way. In order to do that, we just flip this. We're going to put the x over here, and we're going to put the -2 over here. But what about this inequality? Does it stay or does it also flip? Well, notice that this large end here is towards the x. It needs to stay that way. So if you flip those, you do have to flip the inequality in order for it to be the same statement. X's are bigger than a -2. X's are larger than a -2. It is just easier to graph. All right, so what we're going to do, there's 2 ways we're going to graph. One way is using a circle, an open circle, that some of you may be used to, and then we'll look at the way Pearson's going to do these. What we'll do here, what some of you may be used to, is our number line. 1, 2, -1, -2, -3. All right, so we're going to deal with these separately. And then we're going to look at the conjunction or the intersection of them both. Now, some of you may have learned that you go to the -2 and you put an open circle above the -2. The reason you're putting an open circle and not a closed circle is because you don't have this bar, which means equal to. They're just greater than a -2, but not equal. So we use an open circle, and then it goes in this direction. Okay. This one, x is less than 1. You go to the 1. It's also an open circle because there's no bar. And we want x's that are smaller than 1. So our arrow is going to go to the left because numbers that are smaller than anything is always to the left. Okay, now we're not done yet. What we now look for is actually it's like having these 2 separate ones. Now we're looking for what's in common between those. And looking at that, What's in common is this section here between a -2 and 1 is where you've got both graphs. So our solution then, if we were to graph it using this type of notation with the open circle, we would have here to here as our solution on our number line. Now, Pearson doesn't use this type of symbol as far as an open or a closed circle. We're going to look at what they do, and then we'll put it into interval notation after we get these graphs all straightened out. All right, rather than an open circle, we're going to do this one first. Pearson uses a parentheses. So the graphing and the interval notation go together. If you remember from our last section, this, if you have parentheses, either one, it means not equal to, like less than or greater than, but not equal. And if you had these bars here, that's when you had the equal, like less than or equal, or greater than or equal. Okay, you have these bars under here. So these correspond to our marks on our graph. So in looking at the -2, I'm going to choose a different color. Maybe I'll use this red one that works. I hope so. In graphing this one here, you go to a -2. Now you're going to use a parentheses because you don't have the not equal. You don't have that bar underneath. And which way is it going to go? Well, you want x's that are bigger. So you're going to be going to the right, so your parentheses goes to the right at a -2, rather than an open circle, parentheses. So this corresponds to an open circle, and these correspond to closed circles. Okay. Now we want x's that are bigger than a -2, so it's going to go to the right, this way. Okay. Now, another thing you can also look at is if the variables on the left, this arrow that you're drawing corresponds to this right here. See, they'll match. This one's pointing this way, it'll point. But it's really important to understand that we want x's bigger than a -2. And we want x's smaller than 1. So we're going to go to our 1. And I guess I can go ahead and do it in the same color. Now here we have a parentheses. Our x's are smaller, so they're going to be heading in that direction. And we want x's less than 1. Now, where are these both graphed? Both of these are graphed. You went greater and less than. This section right here is what they have in common. Both of these graphs have in common. And it's it's a conjunction, so we wanted what's in common. Now, how do we write that in interval notation? This is what the graph will look like on Pearson. Numbers between -2 and 1. Greater than a -2, x's are greater than a -2, and x's are less than 1. Okay, that section there is what was in common. Now, interval notation, it would be, you go to the furthest left on the graph, which is a -2 to 1. And there you go. That is the interval solution, interval notation solution between -2 and 1. That would be the common between the two graphs. We kind of explain that in detail up here. But this is interval notation, but it doesn't mean sometimes you may have to know the set notation. And so using that, even though it didn't ask, just kind of a side, we could do the set of all x's such that they may put x as a real number and x, oops, I got to give myself a little bit more room. These conjunctions between two numbers, -2, okay, is less than x is less than 1. So x is between -2 and 1. Our x's are between. This is the graph of the solution, interval notation for the solution, and the set notation for the solution. All are right. Pearson will want a specific one. All righty. So these are called a compound sentence, and they can be written like this, where X is between two numbers, or interval notation. X is between a -2 and 1, but not including the -2 and 1. All righty. Now let's look at this note that's down here at the bottom of this page. A conjunction of the form A is less than X and X is less than B can be combined and abbreviated as X is between A and B. That's kind of what we ended up with here. All right, your X's are between A and B. Now, you could also write it with greater than symbols, but to tell you the truth, this is the main one that we'll be using in this class. Where we use it with less than symbols, this will be the smallest number, A, and this will be the largest number, B. It's not that these are wrong, but writing it this way, it's just that this is the way you'll probably see it. Normally, if I'm given this, I change it to this. All right, that's just easier to look at. Now, this can only be done if the inequality signs are pointing in the same direction. So if you have a greater than, you cannot have a less than. If you have a less than, you cannot have a greater than. They have to be the same. They have to match if your X is between two numbers. All righty. Hopefully that made some sense. Okay, let's look at another one. We're going to go through a bunch of examples for those of you that might find this confusing, this concept confusing. Again, graph and write the interval notation for the conjunction X is less than or equal to 2 and X is greater than a -2. So we're looking for a conjunction, an intersection. We're looking for what's in common between these two graphs here. We'll start, I guess I really didn't need this big of a graph, but that's all right. -1, -2. We'll do these in different colors, and that might help you to see. I'll start with a red and maybe green. Okay, we'll start with this first one. X's are less than or equal to 2. So we're going to go to the 2, and you need to decide if you're going to use a symbol like parentheses or if you're going to use the brackets. Can you see? Yes, you can see that. So here, because of the bar, we're going to use brackets. Now, which one? Do we want our bracket to come open to the right or to the left? Well, here we want X's that are less than or equal to 2. So when we go to the 2, X's that are less than will be to the left. So our bracket is going to go this way. And our arrow will go this way. So the bracket's the same direction as the arrow. Okay. Now we'll use a different color. I'm going to try this green. Oops, excuse me. Make sure it works. Yes. Okay, now for the next one, move this down a little bit. We want to go to a -2. So you go to the -2 on the number line. Now this one does not have the bar, it doesn't have the equal, so we'll be using a parentheses. Now we want X's that are bigger than a -2. So when we go to a -2 and numbers bigger are always to the right. So our parenthesis is going to open this way, and I'm going to put it a little above the line. All right, just so that we can see the difference between the two. Now, what's in common? That would be the solution. That would be the graph of the solution. Our solution then would be this section here between the two numbers. It has both a red line and a green line. And in a conjunction or an intersection, you want the commonality. What do they both have in common? What section? So our solution is going to go, we'll just do it in green, -2 to 2. That would be the graph of the solution. But, it would be on the number line itself, but you can get the idea. Now, interval notation, how do we write this in interval notation or solution? We write -2 is the furthest to the left, and we go to the number 2, and we have to use the appropriate symbols. The -2 is not included. I didn't have the bar, but the 2 is. This symbol means the 2 is included, and any number in between. So that's interval notation, which is what they asked for. if I were to write this in set notation as a compound inequality, it would be a set of all x's such that x is any number and x is between, I'm just going to put those symbols there, the smallest number here, the largest number here, but the 2 is included, so I have to put the bar underneath that one. So x is between -2 and 2, not including the -2, but including the 2 for your set notation. Again, 3 ways of writing the same solution. Let's look at another one. We want the conjunction between these two. X is less than or equal to a -3 and x is greater than 1. So we want the conjunction or the intersection or what's in common. Let's graph both of them. We have 0, 1, 2, -1, -2, 3, -4. Okay, we can do the red and green idea again. Let's go ahead and do this first one. The x's are less than or equal to a -3. So we're going to go to the -3. We have an equal, so we're going to be using a bracket when we get to the -3. I want x's that are smaller, small and pointing towards it. X's that are smaller than a -3 are to the left of a -3. So that is the graph of that part. X's are greater than 1, so we'll go to the 1. This is a parentheses because it doesn't include it, and we want x's greater than 1. Now, this is a conjunction, which means we want what's in common between these two graphs. And obviously, there's nothing in common. This is over here, this is over here. There's not the same. There's not a cross in there like this one up here, where we had a common area, which was the same. So here, this is a no solution. So it could be, depending on Pearson and the problem, it could be no solution. They could spell out empty set. There is no solution in the solution set, it's empty. Or you could use the symbol, empty set. So they have nothing in common. These two graphs have no section that is in common. And so you would have the empty set or no solution. All right, so that kind of deals with conjunctions, and we'll come back to the idea. But we're going to look at our second idea, and then we'll review both of them. And the second idea deals with unions, and it has a different symbol. It's similar to the intersection, but this union of the sets A and B is the collection of all elements that are in A or in B. So what you're doing, rather than looking for what's in common, you're just combining the two and making one big set. You just combine them all. Whatever's in A, whatever's in B, and make them one big set. We denote the union of sets A and B as this right here. So this is not hard. The problem is remembering that this symbol means intersection. Oh, wait a minute, I just went blank right there. So you have an intersection between the two. What's in common, sorry. Or this symbol right here, where you're just combining them. You just have to remember those two. So you have an intersection. You could think of it as like this is kind of more of a closed type area. And so it's going to be smaller. This is an open, so it's going to be a little bit larger. But we have this as a union symbol. The union corresponds to the word or. So just like we had intersection was common and it was the and, the or is used with union, and it's a collection or combine all of them. Also, the use of the word or to join two sentences is also called a disjunction. So we have a conjunction, intersection, common, and I can put conjunction here. That's that symbol. And then we have the disjunction or union, and it's got this right here symbol. So let's just kind of go through some examples. Find the union of these two sets. Well, all you do is you have a 2, put it in. There's a 3, you put it in. There's a 4, you put it in. There's a 3, but you've already got it. So you don't have to, no repeats. If you got it once, that's all you need. 5 and 7. So whatever appears in these must appear here in the solution set. So the solution set is 2, 3, 4, 5, and 7. Okay, let's look at another example. All right, find the union of A and B, where A is equal to this set and B is equal to this set. So we're going to find the union. So our solution set, and again, I don't know if you'll have to put the brackets in or Pearson will do it for you. We have 2. We have 4, 6, 8, 10. I'm just listing them all in that first set. This, like I say, sometimes Pearson may want these in order. Sometimes they won't. 3, yeah, we don't have it yet. We do have the 6, so we don't have to write it again. 9. We have the 12, so we don't write it again. And we have 15. So this is the solution set. This is the union of A and B. It's just a little bit bigger. Awesome. You're doing great. All right, let's look at graphing with inequalities with a disjunction or a union or an or. All right, both of these are on the left. So we're going to look at 1, 2, 3, 4, -2, -3, and -4. All right, we'll start with this first one. We're going to graph it separately, then we'll graph this one separately, and we'll combine the two and look at the interval notation, which it's a little bit harder than the other one, but it's not too bad. We're going to go to a -3, and we need to decide if we're going to use a bracket or a parentheses. No equal underneath, so we'll use the parentheses. And we want x's that are less than, which are smaller than a -3. So our parentheses will go here, and there's that one. Now we'll go to the other one. We have x's that are greater than 3. So we go to the 3. Again, it's a parentheses, not a bracket, because there's no bar, there's no equal. And we want x's that are larger than 3. So go to the 3. Anything larger is always to the right. And again, this arrow's going this direction, this arrow's going in this direction. Okay, now if we wanted what's in common, it's a no solution, but that's not what we want. We just want to combine the two. So the graph of the solution is actually this right here. That is the graph of the solution. But the interval notation, how do we write that? It's a pencil. The interval notation, you do the sections separately. We have a -infinity, because this arrow is going left forever, to a -3. And it's a parentheses. It's not included. So this right here is the interval notation for this section. -infinity to a -3. This section goes from 3, the left side of this section is 3. The left side of this section was the -infinity to infinity. All righty. Now, what you're going to have to do in Pearson, when you write this here, you will have to have, I'll just rewrite the whole thing. Oh, I must have an 8 on an infinity. So we have a -infinity to a -3. You use your union symbol between these two sections, or Pearson count it wrong. Now, this symbol here will appear as a button that you can click on the bottom. So this, like the fraction key appears, this will appear. This is the one we'll use the most. not the intersection one as much. But we'll be using that union. So when you have two intervals and there are two different sections, always put the union symbol in between them in order to get it right, not a comma. Unless they tell you to put a comma, but generally it's the union symbol. Now, in order to write this with set notation, so we did graph it, all right? We did find the interval notation. Let's go ahead and find the set notation. How do you write the set notation for this one? This is x's less than a -3. It'll match this right up here. And this right here will be x's greater than 3. And what we do instead of a union symbol, when you're doing this, you would write x is less than a -3, or use the word or in there. X is greater than 3. So you can either do here or here and then graph it. All right, let's do another one. Graph and write the interval notation for the disjunction. Again, so we're just going to be combining. We're not looking for what's in common. It's a union. X is greater than a -1. 4, 5, 6, and -1. So we'll do this one first. We'll graph this one and then we'll combine the two. I'll do them in different colors. Here we have x is greater than a -1. Well, x is greater than a -1. Start here and they go to the right. Okay. I'm going to use a different color for the other one. X is greater than 5. So we're going to go to a 5 and use a parentheses. And they also want x is bigger than that. So if we wanted an and, we would, if this had find the conjunction, this would be our answer from 5 on, 5 to infinity. But excuse me, that's not what we want. We want a disjunction. So we're just going to combine it, the largest one here. We're going to go from a -1 to infinity as our solution. So the graph on Pearson would start here and go this way. That would be the graph of the solution. And the interval notation would be -1 to infinity. All right, that would be the interval notation. The set notation would be x's greater than a -1. The set of all x's such that x is greater than a -1. Okay, so I'm hoping that kind of makes sense there. I wanted to make sure that when we did these, yeah, x's are, yeah, all right, good. Let's do another one. Graph and write the interval notation for the disjunction union. X's are greater than 0 or x's are less than 8. Let's go ahead and we're going to graph. We've got 0. I'll give us a little bit more room on the positive side. 1, 2, 4, 5, 6, 7, 8. Let's put a mark for 9. Let's start with the first one. The x's are by themselves and the x's are on the left. So there's nothing to do but just to graph them. We'll graph this one. We have x is greater than 0. So I'm going to do this one. It's a parentheses because there's no bar. And we want x is greater than 0. So it's going to go in that direction. We want, go to the 8. We want x's that are smaller than 8. Let's do a different color. So here we go to the 8, but we want x's less than that. So that's going to be to the left. I'm just going to put it above the number line. Now, if we had a conjunction or an intersection, our answer would be between 0 and 8, because that's the section that has both in common, both graphs in common. But this isn't what they're asking. They want a disjunction. They want us to combine the two. Well, notice that when we combine the two, everything's graphed. There is not a section that's not graphed. This takes care of everything over here. This one takes care of everything over here. So our solution is actually the whole number line. Okay. The whole number line from negative infinity to infinity. All right. That would be the interval notation for that solution. It's everything when you combine the two. Or in set notation, you would just write all real numbers. Okay, that's how we would write that, all real numbers. Okay. All right, now they do have a note down here at the bottom of this page, because we've talked about conjunctions, we've talked about disjunctions. We're going to add one more step, basically the same, just a little bit of solving for x's. But for disjunctions, you cannot abbreviate as one statement. Okay, what does this mean? I want to look back. What do they mean by one statement? This is what they mean by one statement when you combine them into something that looks just like this. You cannot use this for a disjunction ever. So when you have a union, you will not write it like this, okay? That's what they're talking about here. You can write it, let's see, for example, if you have the statement x's are less than a -4 or x's are greater than or equal to 2, you may not write it like this. When these are less than, the small number always has to be over here and the 2 has to be over here. Just remember that when you have these statements with the or, you have the two sections and you'll have the union. Let's see. It's on the one I'm on right now. So if you do have these two sections here, you can write it the solution like this, or you keep them separate with the word or between them. You can't write them as a single compound statement. That's only for our conjunctions. So that's what they're talking about there at that note. So now what we're going to do is we're going to get the x by itself. So now we have to do some more steps. Up to this point, you've always had the x by itself on the left. Now we need to get the x by itself on the left. When you're solving an inequality, it's just a glorified equal sign. And the only time it's different than an equal sign is if you multiply or divide by a negative. So here, when solving an inequality, if you multiply or divide by a negative number, you must change the direction of the inequality. I usually say you just flip the inequality. Well, let's look at an example of this in this first one right here. We need to get the x by itself so that we can graph it and write the solution in interval notation. So let's go ahead and go through that. Two-step equations, pretty simple. Subtract 7 from both sides. -3x is less than or equal to -6. Now you don't flip the inequality when you're adding a negative. It's only when you're dividing or multiplying. So let's look here. Divide by a -3 to get the x by itself. Divide by a -3. So we now have the x, negative over negative is a positive x. But because we're dividing by this negative number, I'm going to flip this, greater than or equal to 2. So, it's just something you have to remember to do. You've got to flip that inequality when you divide by a negative or multiply by a negative, which we'll be doing later on. Let's go ahead and get the x by itself over here. And I do like having the x on the left. So if it ends up over here, just flip things. And also, when you flip the sides, we talked about this. This will also flip. But let's go ahead and get the x by itself. We add 4 to both sides. So we have 2x less than or equal to 14. Then you divide by a positive 2. We're not going to flip the inequality. It's going to stay a less than because we did not divide by a negative. We divided by a positive 2. So x's are less than or equal to 14. Now, once you have this, you need to look at this word right here, between the two. And that tells you if you want what's in common or if you just want to combine. This tells you if it's a conjunction or a disjunction. It will tell you if it's an intersection or a union. And is an intersection. You want what's in common. So we'll graph them and then we'll take the section that's in common. So looking at this, oh, sorry, I put 14 and I meant to put a 7. Sorry about that. There. Okay, thought that was a little bit large. We've got -1, 0, 2, 3, 4, 5, 6, 7, and then 8. Let's do the 2 first in red. We're going to go to the 2. We're going to have a bracket this time. It's been a while since we've had a bracket. Because of that bar, that equal sign, we'll be using a bracket. We want x's that are larger than 2. So our bracket, and we're going to go to the right. Okay. Those are the numbers that are bigger than 2. It's to the right. Then we're going to go to the 7. Again, we have a bracket, and we want x's that are smaller than 7 to the left. Oh, let me get it in green. And it's going to go this way. We go back to this, it's an and, we want what's in common, which is in the section between the 2 numbers. So the graph of the solution, I won't put it on the number line, I'll put it below, will be between 2 and 7. That would be the graph of the solution between those 2 with brackets. Now, interval notation, we go to the 2 to 7. Okay, there's your interval notation. All numbers between 2 and 7, including 2 and 7. Set notation, we would have x's. We have bars between the smaller numbers always here, when you have these less thans, and the larger numbers here, when you have the less thans. Otherwise, you'd switch them. If you switch these, you switch the numbers. Okay, so you've got your set, and you've got your interval, and you have your graphical solution. And we just had to do some basic algebra here, up in here. All right, let's try another one. Make sure everybody's understanding. Again, this first one, get the x by itself. Get rid of what's being added or subtracted first. So we're going to add 5. Add 5. So 2x greater than or equal to 5 and -3 is 2. Nice. Divide by 2. We're dividing by a positive number, so we're not going to flip the inequality. Let's do the other one. Let's see, subtract 2. It's nice that they're having these come out to be good numbers as far as integers. We have 5x left. Those are gone. So far, greater than or equal to 15. All right, divide by 5. Because we're dividing by a positive, we will not flip the inequality. And this next part is important. What do you put in between? What are you looking for? Are you looking for what's in common, or are you looking for an or where you just combine? Well, this is an and, so it's an intersection. It's what's in common. Let's go ahead and graph. I'll just put the numbers on. 1, 2, 3, 4. Yeah, didn't know that. Let's red. X is larger than or equal to 1. So we go to the 1, and we want numbers that are greater than. So we're going to be going to the right, the number 1. X is greater than 1. Then here we go to the 3. Again, it's a bar. and we want x's, I almost did it the other direction. I'm going to do it in green. We want x's greater than 3. So we wanted them greater than 1 and greater than 3. This is an and. What section is in common between both graphs? Well, it looks like it's this section over here from the 3 on. So our graph of our solution, what's in common, will go from the 3 to the right. That would be our solution. And interval notation, you would start at the 3 and include it and go to the right without stopping, which would be infinity. Set notation, x is greater than or equal to 3. And they would probably have the set of all x's such that. Sometimes they'll put that x is a real number in there as well. Okay, that line is read such that. Okay. Interval notation, set notation, graphical solution. All of these are solutions. Let's do another one. Hopefully you are catching on. Again, let's get the x by itself, two-step equation to solve these. Starting with this first one, add 3. Add 3. 2x is greater than 4. Divide by 2. X is greater than 2. Done. We didn't flip because the inequality because we divided by a positive. Let's go to the next one. Add 1. We have 3x. It's gone. Less than 3. Divide by 3, a positive, so we will not flip our inequality. X is less than 1. And this is an and. What's in common between the two graphs, if anything? We'll see. Let's go ahead and graph these. We've got 0, 1, 2, 3, and a -1. Let's graph the first one. X's are greater than 2. We're going to go to the 2. And we're going to use a parentheses. There's no bar, so we're not going to use the bracket. X is bigger than 2 or to the right. Okay. And let's do the other one. X is less than 1. So we're going to go to the 1, and we want x is smaller than 1, which goes to the left. Make sure I copied it down right, because it looks like there's nothing in common. And we were looking for what's in common because we had the word and not the word or. If it was or, we'd have a solution, but we just combine them. But we don't, so this is the empty set, right? There's nothing in common. Great. Let's do another example. Now it looks on this next page that we're to the ors between our two equations. So now we'll just be combining. Again, this is the same first step. We've got to get the x by itself. We're going to subtract 7. 2x is less than a -8. Then we'll divide by 2. X is less than a -4. This one over here will subtract 13 or add a -13, however you want to see, say that. -5x is less than or equal to, for some reason I thought that was a negative there, -10. Okay. Now we'll divide by a -5. So since we're dividing by a negative this time, we do need to remember to flip the inequality. So rather than a less than, it's a greater than. -10 over a -5 is 2. So those are our two. We can graph them, and we do know that this is an or. So we'll just be combining whatever. We'll have a solution. We're going to have a solution with these. The only one you won't have a solution with is if it's the last one that we did. There was nothing in common. Let's go ahead. Here's my pencil. We'll put it 0, 1, 2, -1, -2, -3, -4. Let's start with the -4. We want x's that are smaller than a -4, not including, so we're going to use a parentheses, not a bracket. X's smaller go to the left. So it goes in that direction. This next one, I'll just go ahead and use red. We have x's that are greater than or equal to 2. Well, because we have that equal, we're going to use a bracket. Let me go ahead and put marks here. So we're going to go to the 2 with a bracket, and we want x's bigger, which is always to the right. Now, when we combine these, this is what we get when we combine them. That is the graphical solution right there. The interval solution is going to be -infinity to a -4, not including the -4 and never the infinities, unioned with 2 is where we start in that section and we go to infinity. So that would be the solution to that. So this is the that's the solution, that's the interval notation for that graphical solution. Now, if you wanted to write it in set notation, this section is x is less than a -4. It actually it will be this right here. It'll be this. Or we don't use the union symbol, we use the word or. X is greater than or equal to 2 for this section. It will match in this case. So those are all different ways of writing your solution: graph, interval, and set. All right, let's try another one, an or. I know we go through quite a few examples, but sometimes people struggle. We want to make sure you understand. Okay, now on this one, we need to get the x's by themselves. Good thing I have another pencil. Lots of them up here. All right, so here we're going to add 5. Add 5. -2x, 5's are gone, or less than 3. Okay, well, you can have a fraction, it's okay. We'll divide by a -2. And remember to flip our inequality. And Pearson generally likes to have you leave it as a fraction. It doesn't matter where you put that negative as long as it's there. You can put it in the numerator with the 3. You can put it right even with the fraction bar, or you can put it with the 2, as long as you have 1 somewhere. Now let's go to this other one. Oh, this is only a 1 step. We have x is less than -7. Yeah, all right. And this is an or. I'm gonna write or, and I'm gonna write this one down even with that. So let's graph it and see what we've got. Let's do this first one. We've got I'm gonna go over here. 0, there's 1. Make sure I have enough room. -1, -2, -3, -4, -5, -6, -7, -8. All right, let's look at the first one. This is a -1.5. So you can always make it a decimal to graph it, just so that you know where it's at. But let me move it up a little bit. X is greater than, but not equal, so it's a parentheses, -1.5. So we'll go to a -1.5. It's a parentheses, and we want x is bigger. So it's going to be this way. Or this one, we go to a -7. It's a parentheses. We want x is smaller than a -7. So we're going to go to the left. Since it's an or, there's your graphical solution. You just combine them and that's what you get, is a combination of the 2. Now, interval notation, I'm going to write it above. This section is a -infinity and stops at a -7. Unioned with this section starts and not equal to -3/2, and it goes to infinity. So there would be our interval solution. Set solution is right here. Just write them separate. X is greater than this, -1.5, or X is less than a -7. Interval notation, graphical solution. Hopefully you guys are catching on. Great. Okay, let's try another one. Here. This one might be the last one before we go, to the last page, which is a little bit different. All right, now on this one, we're going to go ahead and we're going to add 11. So we've got 3x is less than 15. Divide by a positive, so we will not be flipping the inequality. This one, subtract 9. 4x is greater than or equal to a -8. Divide by a +4, which gives us x is greater than or equal to a -2. And this is an OR. Let's look at this. Let's graph this and see what we've got. Hopefully it's staying in focus. We've got 0, -1, -2, and 1, 2, 3, 4, 5, 6. Let's start with the 5. We have x is less than 5, and we will use a parentheses with this one. And we want x is smaller, which is to the left. So we'll be going in this direction. Okay. And the next one is x is greater than or equal to -2. So we're going to go to a -2. And we want x is larger, so we're going to be going to the right. But it's not a parentheses, it's a bracket. I almost missed that bar there. And we're going to go in this direction. And I just kind of put that arrow, I'll put that above that. Okay, we're going to combine the two. So when we combine the two, everything is graph. There's nothing that doesn't have a graph. This green one is taking care of everything going this direction. This red one is taking care of everything going to the left. So your solution would just be an arrow along the line this way. That would be the solution. All numbers. Interval notation. We would write -infinity to infinity. That would be our interval notation solution. Or for a solution set, this would be one of your choices. All real numbers. Okay, perfect. We just have 2 more to go. These are compound sentences. Let me defocus it. All right, we're going to go ahead and solve this, and then I'm going to take care of those arrows because we've got greater than and greater than, and we're gonna flip them. But let's go ahead and get the x by itself. So our goal is to get the x by itself in the middle. That way it forms what is called a compound sentence solution. Bear with me real quick if I can find that. So in other words, we want it to look like a solution. Like here we had between 2 and 7. We want it to look like this. I want the arrows in this direction, and I want the x by itself. That's our goal. So let's go ahead and go through the steps. It's really not that hard. Here I'm going to copy it over just so I have more room. It's kind of little. All right, we're going to get rid of the 2 first. Again, we want the x by itself. And the reason we're getting rid of the 2 is because that fraction bar is over both the x and the -1. Normally, we get rid of what's being added or subtracted first. But in this case, we're going to get rid of the 2. And now it's a divide by 2. So we're going to multiply this by 2. And whenever you do that, you're going to multiply all three sections by that. So we have three sections now. And whatever you do to one section, you do to the other two sections on both sides. All right, so it's actually not too bad. That way these cancel. So we end up with 6 greater than or equal to x minus 1 greater than or equal to negative 8. All right. Now we need the x by itself. Let's get rid of the 1. So you add 1 to each section. Plus 1, plus 1, plus 1. 7 greater than or equal to x. This is gone. Greater than or equal to negative 7. Okay, like I said before, this isn't wrong, but it's just a little bit more awkward. So we're going to flip this so that we have less than symbols rather than greater than symbols. So we're going to move the negative 7 over and this positive 7 over. I guess I'll just do this in pencil. So we're going to have the x in the middle, and we're going to have the negative 7 and the 7. When you do that, you flip the inequalities. So we have x's. Notice that it really is the same. Here we have x is greater than a negative 7. X is greater than a negative 7. X is less than 7. X is less than 7. This is just easier to say because we can read this. X is between negative 7 and 7, including negative 7 and 7. This is a compound, and this is used for our ands sometimes if the solution works out. Not all ands look like this. And we did some examples where they didn't. But this is one possibility for an and, a conjunction, or an intersection. Let's graph it. Do we have to? Yeah, solve and graph. All right, so that's one way of writing that. Using interval notation, it would be negative 7 to 7. Okay. So we always have the smaller number on the left and the larger number on the right, and these pointing less than, less than. So we go to 0, 7, 6, negative 7. So our solution is between those. So including those. So we'd go here all the way over to the 7, including. So you use brackets. It's really not too bad. Really is not too bad at all. Let's look at our last one. Wow, this is awesome. Our last one. It's got some tricky parts to it. I'm going to copy it. I'll just copy it down here. I think I'll have enough room. Negative 10 less than or equal to. I'm just going to give myself a little bit more room to show you what to do. All right, just like before, we got rid of the positive 2, sorry. Now we're going to get rid of the negative 3. And we're going to multiply all 3 of our sections here by a negative 3. I'll put it behind here. So times a negative 3 over 1, you can think of it that way, times a negative 3 times a negative 3. So our answer then, I guess I can do it in green, is positive 30. All right, here's the tricky part. I multiplied by a negative 3. When you multiply inequalities by a negative or you divide by a negative, you flip the inequality. So we've got positive 30, but this is going to be greater than or equal to. These cancel. They're gone. All right, the negative 3 is gone, and we're just left with x plus 6. We have to flip this inequality for the same reason. We're multiplying through by a negative 3, which gives us a positive 24. So hopefully I did not lose anybody on that step. If you multiply by a negative or divide, in this case we're multiplying, you flip your inequalities. Now, those interesting little dots on those bars, but that's okay. Last thing to get rid of is the 6. So we're going to subtract 6. So we have 24 greater than or equal to, the x is by itself, we've reached our goal, greater than or equal to 18. I just don't like this written this way. I'm gonna swap the inequalities. So we've got x, I'm gonna put the 18 over here and the 24 over here and flip our inequalities. So we've got x is greater than or equal to 18, x is greater than or equal to 18. X is less than 24, x is less than or equal to 24. This one's easier to read. X is between 18 and 24. This is a compound sentence. All right, so our solution is between 18 and 24. So if we had our, I'm not going to put, we're going to have 0, few numbers, we'll have 18, and we'll have 24. And we want numbers between 18 and 24 graphically, and including the 18 and the 24. So there would be your solution. X is numbers between 18 and 24. This is a compound. It's your set notation using inequalities, and your interval notation would be 18 to 24, and you're including those numbers. Awesome, we're done. Well, if for some reason things were confusing, let me know. Otherwise, good luck on your homework, and thank you for watching.